Now we'll cover some practical aspects of using an HPC machine that are often overlooked but very useful. So in particular, we're going to look at batch system, or scheduler as it's also called, and parallel application launchers. So I'll give a bit of conceptual background into what schedulers do and why we have them, some things that are in common between different scheduling systems, and I'll say something about how HPC applications are actually launched on the machine in parallel. And further on in other sessions, you'll get a chance to actually play around with this concretely. So this will be a general introduction. So to start, what is a batch system or a scheduler? Really, it's just a way to make sure that different users, of which there are many on a given system, are able to use the computational resources that are available in a fair way. So it's some kind of mechanism to control access to make sure it's not a free-for-all. And essentially what it comes down to is some kind of queuing system for users' jobs. So in that there are two aspects involved, which is that it manages the reservation of resources for these jobs and actually shepherds the execution of these jobs as they take place. This is not only simply a means of controlling access, it's just also very sort of the batch aspect is a very useful aspect of schedulers, of batch systems, because what it means is you can describe perhaps quite complicated large sets of simulations that you want to perform or calculations you want to perform, and then set these running and then come back to them later once they're done without needing to do anything while they are working. So I already said we need a batch system to make sure access is mediated. Conversely, if you look at this on the flip side, actually part of the things that schedulers do is they try to make sure the system is utilized as efficiently as possible so that people's jobs are packed as efficiently as possible, which is good for everyone, good for the system, good for everybody trying to use the system. It's also a way to keep track of accounting and budgets, so compute time that's being spent by people, and as well as mediating the access to actual computational resources, i.e. processing compute time. It also is used to mediate access to things like software licensing. So it's kind of a general management and aspect of using an HPC system, and you can't get around it. It's very, it's one of the first things you do if you want to run a job. You interact with the scheduler often in some way. So how do you use a batch system? Well, there's a couple of ways. You typically write a job script that specifies what resources you need and then what you actually want to do with those resources. Then you submit that job script to the scheduler. It goes into a queue, and then whenever there is at some point appropriate resources available, the job will execute until it either finishes successfully or fails or exceeds some kind of time limit, and then you look at any outputs and errors. So broadly speaking, this is kind of the flow, pretty much as I said. So while the job is queued and executing, you can check the status. And some systems even provide a web interface to do this, or can alert you via email on the status of your job. So some concepts. There are some concepts that are common between different scheduling systems. There's a concept often of something like a queue or some kind of logical scheduling category, namely that there's not just one kind of access to the system. There's different kind of access which is based around, for example, things like different time constraints, the number of nodes that you can request at any given job. That might be you might have a separate queue for people who are waiting to get a large number of nodes or a small number of nodes, or people that want to use particular features of which there are only a subset of nodes, like nodes with a lot of memory or GPUs, for example, nodes that are reserved, for example, for this training course, so that only users who have the reservation code and are authorized can use those nodes, and they're set aside. And I guess it goes without saying that when you're queued with other people waiting for the same thing. So jobs within a queue, they they're scheduled to share usage of the resources associated with the queue that they sit in. Now, on Archer, on the predecessor to Archer 2, there were, for example, there was a short queue which was to do with a certain kind of maximum duration of jobs, maximum number of nodes that could be involved. On Archer 2, similar things exist, something similar exists, but it's not called a queue. It's to do with it's phrased in terms of quality of service, as will be clear from the concrete session and that Julian is running, and also the practical. Another common concept in batch systems is the concept of priority. So the scheduler has to assign some kind of priority to jobs that on the basis of which it decides how soon they will start. An account name or budget code, often there will be something that some numerical code that identifies the charging. Ultimately, compute time equals money, so somehow that needs to be accounted for. So that has to be specified when you run a job, when you write your job script. And the wall time as well, which is you specify the time that you expect the job to take, which is in a sense a resource request. It's a resource request, not in terms of well, it's just one dimension. I mean, the number of nodes would be one dimension, the number of cores is one dimension, and the amount of time for which you want them is another dimension. An overview of some common commands. I already hinted, there are different schedulers in existence. Archer, the predecessor to Archer2, used to use PBS. Archer2 uses SLURM. There are similar concepts, similar commands, but they're just called slightly differently, but they do similar things. So QSub on Archer is SBatch on SLURM, and you'll see these coming up in the practical and then the concrete session that Julian's running. When you examine the status of a job, there's various statuses that it's in. So it could be queued, or it could be running, or it could be busy exiting and cleaning up. So there's various codes depending on the scheduler in question that are associated with that. As well as PBS and SLURM, some other batch systems are Torque, Grid Engine, SunGrid Engine, SGE, and LSF, as well as Load Leveler. And these have sort of different features. Some of them can do clever things with booting up different nodes when they're needed, for example. These are constantly being developed. SLURM is nice because it's kind of it's an open source one. So it's often used to experiment with new features that are incorporated into SLURM later, or into other schedulers as well. Now, I won't go into much detail with regards to the actual job script examples, because there are concrete sessions on that. But broadly speaking, there are always two sections: a header that specifies resources, and then an actual parallel application launcher command that specifies what you want to run. Similarly for SLURM, a similar idea, but just the terms are different. The syntax is a bit different, but again, you have two sections, one section with a resource request, another section with a parallel application launchers, and I'll get to parallel application launchers in a minute. So in this case, you can see for this particular example, which is not Archer2, the concept of a partition with a -p option was used to specify access to a queue that gave access to nodes with GPUs. As well as these batch jobs, which specify where you write job scripts that specify simulations that you want to be executed without, you go away and it executes. Many schedulers allow you to run interactive jobs where you give a resource request for similar kind of thing that you would do if you were writing a batch script. You would say what you want in terms of time and number of compute nodes or any other resources, and then you used it interactively. So you need to be ready to use it when it becomes available. It typically gets scheduled, and then it might, it's not necessarily available to use. Those resources are not necessarily available to use right away, but you may have to wait. You may wait to get an email to notify you, and then quickly go to your terminal and use these resources. This could be very useful for doing testing, debugging, looking at the performance of code. It's typically when you're trying to figure out stuff without wanting to commit to running big, long jobs yet. It could be for visualization of results, possibly, or analyzing data. How this actually works, it really depends and varies from machine to machine. but it's quite common for HPC machines to have some nodes that are dedicated to interactive work to be able to do this, to have this available quite quickly. Good practice is if you're using a scheduler, writing jobs, job scripts, do short jobs. Well, first of all, you can use an interactive session to test that what you're planning to run works, and it's just a very quick turnaround. You can get immediate feedback, much as if you're running something on your laptop or a desktop machine. Then once you're happy things work, prototyped it, then you write your job script. And one thing that's useful to keep in mind that in JavaScript you can use lots of functionality from shells like Bash that you may or may not be familiar with. So there's a lot of functionality that you can use there, so one of the things that's useful, good practice to do as well, is to specify wall times that are realistic but not overly large, that the scheduler can make a good estimate of the time to assign to your job. When it comes to scheduling, it's useful to understand a bit. I mean, it can be very frustrating if your job doesn't run, you have to wait, but it's useful to understand a little bit about what schedulers have to do to schedule jobs. It's kind of a multi-dimensional Tetris game, because each user has specified the resources their jobs require, and then so here the point is that there's a distinction between resource requests and what you actually do with the resources. When you get a number of nodes for a certain time, you could run one single application on all the nodes that you've requested, all the cores that you've requested for the full time, or you could do shorter runs using each of which uses all the cores, or you could do maybe multiple runs at the same time, each of which use only a part of the cores. So there's this distinction again between requesting the resources and then what you do with them. So going back to the scheduling problem, it's a kind of complex situation actually, because the scheduling algorithms, they try to make use of resources as efficiently as possible, and the situation is constantly changing because jobs that are currently running are either continuing to run or failing or finishing as expected or before their expected termination date based on the estimated wall time, and people are constantly submitting jobs and canceling jobs, so this constantly needs to be recomputed. When I say this, I mean the decisions about what to schedule for future and what to start executing at any given time is constantly being recomputed. Different algorithms a scheduler's algorithm can be tweaked and set up and configured by a service provider to prioritize certain things like waiting times, like trying to make sure that large jobs, for example, are prioritized if that's seen as a positive thing. Even more recently, power consumption is increasingly important. So these kind of restrictions and tweaks to the configuration can have quite a large impact on both the performance of the scheduler, so how efficiently it manages to schedule the system, and therefore how that system is utilized. To give one sense of what's going on is that there's something called backfilling, which is that a scheduler can start by looking at all the jobs that it currently knows about. It assigns them priority according to some scheduling policy. Then it starts with the highest priority job, and if it can currently run, then it would run it. Then checks the next highest priority job, and if that can run already, then run it, etc., etc. Then for the highest priority, the first job that it cannot currently run, it schedules it to run in future as soon as the resources that it needs become available based on what it knows is already committed. And then what it can do is that any lower priority jobs that are maybe smaller or that for whatever reason could finish before the higher priority job that it just scheduled is due to start, it backfills those gaps that it sees to improve resource utilization. So this is just one example, and this is a big area of research really. So now we come to parallel application launchers. So once you have your resources, how do you actually run an HPC application in parallel? So to run applications, so you already have come across a little bit mention of MPI and threads, and you'll see more of this in in the rest of the course. But to run MPI parallel applications, which we said is a big part of running HPC software, you need to use a so-called parallel application launcher. You may be familiar with these if you've used any kind of HPC system before, or even a generic cluster. They would be the commands like MPI run, MPI exec, srun, as is the case on ARCHER2, or AP run, as was the case with older Cray systems. And in some cases, these use information provided by the batch system. This is certainly the case for ARCHER2, where srun picks up a lot of the resource requests that you've provided in your job script to the scheduler. But in some cases, you can specify additional options to control how your application is launched. So what the parallel application launcher does in each case is it launches the desired number of processes, i.e. the desired number of instances of your application, which we expect are going to communicate by passing messages using MPI. And it sets up the whole, the parallel application launcher is responsible for setting up the whole environment, a software environment that allows these processes to communicate. And it's also used to control the way that the processes, well, how many there are on each node and how they sit on the cores, and in combination with processes and number of threads per process, which you'll see in the coming days, and in the practicals as well as the talks. This can be combined to use cores, available cores in particular ways. So what parallel application launchers also control partly are the way that the processes and threads, as I said, are placed on cores, the way that they run on cores, and in fact it in a sense ties them to stick to a particular core. Yeah, so there's a lot of advanced options here. AP run was relevant for Archer, but no longer for ARCHER2. I won't go into any more details because that will be covered in the concrete session, Julian's concrete session about ARCHER2, and you'll also see examples in the practicals about how to do both pure MPI and pure OpenMP and hybrid MPI plus OpenMP parallelism using srun on ARCHER2.